The question we're addressing in this lesson is the following. Why create a histogram in the first place? Why do we care what the shape of a distribution is? The first thing you should recognize, and you know this already, is that different natural processes create or generate different kinds of data. So for example, on a roulette wheel, every slot on the wheel is meant to be equally likely. Thus, when we spin a roulette wheel a whole bunch of times and plot the results on a histogram, we get a distribution that's roughly uniform. Similarly, if we are more interested in the reliability of oil pipelines than simple games of chance at Las Vegas, and we plot the location of pipeline breaks and get a uniform distribution, then we know that each part of the pipeline is equally likely to fail. The distribution tells us something fundamental about the underlying process creating the data. A second and more practical reason we care about the distribution of our data is that if our data fits a known theoretical distribution, we can use that distribution to make inferences about outcomes. Let's see how this works. A couple hundred years ago, a handful of mathematicians recognized that certain natural processes tend to generate data that plot along a bell curve. So they developed a functional specification of the phenomenon, an equation that is written in terms of two parameters, the mean and the standard deviation. So the bell curve, or the normal distribution, or Gaussian distribution, Gauss was one of these mathematicians, is really a family of curves, and the exact shape and location of the curve depends on these two parameters, the mean and the standard deviation. Once we parameterize the normal function, that is, once we know the exact shape and location of the normal curve, we can do something really useful. We can calculate the probability of a value from the distribution falling within a certain interval. Let's say that we have measured a lot of feet and we've concluded that shoe sizes for males in Vancouver are normally distributed with a mean of 9 and a standard deviation of 1.5 sizes. We'll see in a moment that this is pure fiction. We never know mu and sigma in the real world, but let's just pretend for now. Also, I don't really know what an average shoe size is. But this is very useful information if we own a shoe store, because we would be interested in optimizing our investment in inventory. We'd want to be able to satisfy customer demand from our stock so that we didn't lose sales. But at the same time, we wouldn't want to have a whole bunch of money tied up in a bunch of odd size shoes that don't fit our customers. Let's say our policy is to stock shoes in sizes between 7 and 13. If we know which normal curve describes shoe sizes, we can use integral calculus to calculate the area under the normal curve between these two sizes, 7 and 13. The area under the curve is very valuable. It is the probability that a value, for example, the size of the feet of the next customer who walks through the door, lies between these extremes, size 7 and size 13. Of course, we don't do the integral calculus. It is way too hard for this kind of function. In the old days, people had tables that they could use with some effort, believe me, to determine the area under the normal curve. Today, computers integrate these areas numerically and spit out the probability. But it's nonetheless useful to know where these probabilities come from. Now, in addition to calculating probability given an interval, we can work backwards and calculate the interval given the probability. So say for example we have a policy of meeting 95% of customer demand from stock. What we need then is a 95% confidence interval. This interval would be the range of shoe sizes we would have to carry in our store such that the feet of 95 out of 100 of our customers were fitted from stock. Conversely, the probability of stocking out would be 1 minus 95% or 5%. Now, the choice of an appropriate stockout rate is, of course, a business decision that depends on all sorts of things, such as stockout costs, inventory costs, and hard to measure factors such as the reputational cost of being known as a store with poor selection. But statistical inference gives you the tools to translate probabilities or risks into, in this case, something useful and operational like shoe sizes. I should add there are two special intervals that we often see in statistics. Assume that we are interested in knowing what proportion of the population we should expect to have a shoe size greater than some value x. The interval in this case is x to positive infinity. The same with calculating the probability of being less than x. The interval then is x to negative infinity. Let's go back to what I said earlier about not knowing the population mean mu and the population standard deviation sigma. In the real world, we deal with samples of data. Even if we have the records of every phone call ever placed at our firm, we still have just a sample because we don't have data on phone calls that have not yet been placed. When we use our massive sample to estimate the main duration of, say, a cell phone call, it's just that. We are estimating the population mean based on a sample, even though it's a very large sample. So if we go back to our mathematician friends, we see that the normal curve is a really useful abstraction, a really useful idea, but it is of almost zero practical use to us since we cannot legitimately parameterize it. That is where the t-distribution comes in. The t-distribution is like a cousin to the normal distribution. But unlike the normal distribution, the t-distribution is parameterized by the sample mean and the sample deviation, which of course we can calculate from our sample. In addition, the t-distribution has a third parameter, degrees of freedom, which is really just a measure of the sample size. The bigger the sample on which the estimates are based, the more degrees of freedom, the closer our estimates are to their true population values. Now, when our sample size is very large, as in the cell phone example I just used, something happens to the shape of the t-distribution. It becomes indistinguishable from the normal distribution. So what I said above about the normal distribution being useless is not exactly true. If you have a large enough sample, you can use the normal distribution as an approximation. But the advantage of the t-distribution is that it automatically accounts for the size of your sample when making statistical inferences. If you have a large sample, your results will be identical whether you use the normal distribution or the t-distribution. But if your sample is small, you will see that the t-distribution is more spread out than the corresponding normal distribution. And this spread of the t-distribution gives you very wide confidence intervals. So that's not necessarily a good thing, but it does prevent you from making overly precise estimates based on very small sample sizes. So the bottom line, the t-distribution is the correct distribution to use when your data looks to be normally distributed, but when you don't know the population parameters for the normal distribution. Since you never know these parameters, the t-distribution is always the distribution to use when you're doing statistical inference. The central limit theorem is covered in the SAS materials, but it's pretty fundamental to what we do in business decision making, so it's worth a little extra coverage. In almost any business decision problem, your situation is going to be the following. You have a bunch of data in a spreadsheet or you can get a bunch of data from databases. But what you want to do with this bunch of data is to use it to make inferences about the world generally. In statistical terms, you want to use a sample to make inferences about a population. For example, imagine you have some data on a store's sales and you're trying to decide whether you have the right person running the store. The sample of data, the actual daily sales, are quite variable. Some days are really good, some days are really bad. Your job is to determine whether the overall performance is acceptable. So what on earth can one sample tell us about overall performance? It turns out that the answer is quite a lot. The reason is due to the magic of the central limit theorem, which gives us three results. First, the best estimate of the population mean is the sample mean. So we can calculate our sample mean using our well-known formula, and that's going to be our best estimate of the population mean. Second, the sample means taken from the same population are guaranteed to be normally distributed. So I'll talk about this again in a moment, but I should point out that what I just said is only true when we have large enough samples. But we know already that we must be very careful and always collect large representative samples. If we don't commit to doing at least this much, we are wasting our time with analytics. Third, we can use the standard deviation from our single sample to estimate the standard deviation, or sometimes it's called the standard error, of the distribution of sample means. So points number 2 and number 3 are a bit complicated because they depend on this word sample mean. So we'll spend some time on explaining what this means. Let's assume, to keep things really simple, that we are interested in knowing whether a single die is fair. As in the store manager problem we talked about earlier, we recognize that a single roll is subject to a lot of chance and probably doesn't tell us much about the die, doesn't tell us much about the population. So we decide to roll it, say, 5 times and use the sample as the basis for our decision about the fairness of the die. We'll see shortly that 5 is likely too few in a sample, but it'll get us started. A fair die should yield the numbers 1 through 6 with equal likelihood. Thus, if we roll the die 5 times, we should expect a mixture of outcomes as shown here. To summarize this result, we can take the sum or the mean. So the sum in this example is 13, and the mean is 13 divided by 5 rolls, or 2.6. The question we want to answer then is whether this is a fair die. And this is where the central limit theorem comes in pretty handy. First, recall the implications of the central limit theorem. First, our sample mean is the best estimate of the population mean. Now we know, because we know something about dice, that the expected value of rolling a die is 1/6 probability times 1 plus 1/6 probability times 2, and so on, for an expected value of 3.5. You can work that out on your own if you want. Dice and games of chance have really well-defined rules and outcomes, so they're really the one domain in which we can actually say with certainty that we know the population means. In any case, the estimate of the population mean we got from our small sample is only 2.6. So the question is the difference between our estimate and the known population mean too big? And this difference really has 2 possible causes. One is that the die is not fair, and thus the mean value is not equal to 3.5, as we would expect from a loaded die. The second possible cause is that the die is in fact fair, but our estimate of the population mean is a bit off due to random chance when making our 5 rolls. So ostensibly, if we took a different sample, if we rolled the die 5 more times, we would get a different estimate of the mean, and perhaps we'd draw a different conclusion. One way to better understand the role of sampling error is to draw some more samples. Let's roll the same die 5 more times for a second sample. Here the individual outcomes are different, but surprisingly the sum is 13 again. So the mean of this second sample is also 2.6. Every time we roll the die 5 times, we have a new sample with a new sample mean. This number, the sample mean, is what we referred to before when we were talking about the central limit theorem. It is the number that we really care about in all this. So what would happen if we had the luxury of generating a large number of samples? First of all, you should recognize that when rolling a die 5 times, there are many different ways to get a total of 13. So we should not be too surprised that our first 2 samples both yielded a total of 13. However, there is only one way to get a total of 5. Each of the 5 rolls must be a 1. Similarly, there is only one way to get a sample mean, or a grand total rather, of 30. Each of the 5 rolls must be a 6. Anyone who's played Yahtzee or similar dice games knows how unlikely this is. So if we generate a lot of samples, we get a lot of different totals for the 5 rolls. We should expect most of these totals to be in the teens, since there are many different combinations of outcomes that sum to 17 or 18, but very few that sum to extreme values like 1 or 30. So say we run hundreds of samples in this way. We can then plot the sum or the sample means. It doesn't really matter because they're both related by a constant value, in this case the sample size. Here I plot the sample means of about 500 samples, and we see exactly what the central limit tells us we should expect. The distribution of these sample means is relatively normal or bell-shaped. And this is even though the distribution of the underlying samples is not normal, but is known to be uniform, because each face of the die is equally likely. But let's remember the business context here. We don't actually have a bunch of samples in the real world, and we can't plot the sample means to determine that's normal. We have exactly one sample, and that sample has exactly one mean and exactly one sample standard deviation. The power of the central limit theorem is that we can use this one sample mean and this one sample standard deviation to calculate confidence intervals around our sample mean. Now, the usual interpretation of this confidence interval is that we can be 95% confident that the true population mean is within the interval. That is, we can use our sample, our one sample, to make inferences about the value of the population mean and be pretty certain that we've captured the true value.